One of the big concerns in photovoltaic system performance is what's the effect of shading? What if I have local shading from maybe bird droppings or particles, leaves, and so on that might fall on my module? Or what if a corner of a building or a tree shadows my module, or a fence post, or a transmission tower leg, and so on? The concern is very important and very valid. Shading is very bad for photovoltaic system performance. In this segment, we're going to talk about the devices that we use to help get around the negative effects of severe shading. Also, we'll look at the effects of nighttime leakage as well. These are both handled by devices called diodes. A diode is basically a p-n junction, just like a solar cell. In fact, a solar cell is just a big, flat diode. We make very poor diodes. We make very good solar cells. But people that make diodes aren't making good solar cells. They're just making a simple, thick, strong p-n junction. What goes on inside of a diode is very interesting. It's similar to what happens inside of a solar cell. There's an internal electric field set up between p-type doping and n-type doping in the silicon. And this allows current to flow one way, but prevents it from leaking backwards and flowing the other way. Let's take a look at how we use diodes in our photovoltaic system design. Bypass diodes allow just that to occur. They allow current to bypass a shading problem. They do two things for us. They prevent excess local heating at the area of our shading, and they preserve array output. I'm going to illustrate how this happens. Typically, the bypass diodes are wired in parallel with the cells in a module. They're not normally a part of the circuit flow. Under normal circumstances, current's flowing through our cells out onto the next module or the battery, not going through the bypass diodes. But in case of shading, that's when we'll need those diodes. Let's take a look graphically at the effect of shading and how the diodes are needed to kick in. We can look at some cell IV curves and see how they might be affected by shading. We can begin with the IV curve for a single cell. This is not a module, it's just a single cell. This would be connected to other cells in series inside of a module. Those cells might be connected to a shaded cell. We've drawn that shaded cell IV curve slightly lower than the others. A shaded cell can't produce as much current. If we have these cells connected in series, what happens? Let's look at current flow and see how that adds up to give us our composite IV curve. At a low level of current, we would have voltage contributed by the unshaded cell or cells and voltage contributed by the shaded cell. The result would be double that voltage. At a slightly higher current level, we can see that the unshaded cells contribute voltage. The shaded cell contributes some, not quite all the voltage we'd expect from it, but some voltage. So the composite result is almost the full voltage we'd expect from the group. We can continue increasing our current level until we get to a point where we get voltage contributed by the unshaded cell, but no voltage contributed by the shaded cell. We're at its new short circuit point. The composite result is simply the result of the unshaded cell. The shaded cell at this point is no longer contributing to the power output of the string. If we look above this point, we have voltage contributed by the unshaded cells, but the shaded cell now, in order to operate at this high current level, needs to actually operate in the realm of reverse voltage. It can pass that much current, but it does so at a voltage penalty. The reverse shape of our shaded cell can go back many, many volts, more so than the half a volt that it might contribute. So a shaded cell can actually take away much more voltage than it can contribute. The result is that the shaded cell drags down the output of all the other cells connected to it in series, producing a composite curve that's just slightly above the level of the shaded cell itself. The impact of this is quite severe. One shaded cell, or a few cells, but even just one shaded cell, can drag down the output of all the other cells in a complete module, and even the cells in other modules connected to this one module. Let's take a look at the effect of a small amount of shading so you get a sense of the severity of the problem of shading. Let's look at the case of one cell being shaded in a typical power module. We show the standard IV curve under outdoor operating conditions with no shading. Then what if one cell was 25% shaded, 50% shaded, 75% shaded, and completely 100% shaded? You notice that even in the case of 100% shading, if one cell is completely blacked out, the module isn't turned off. So shading doesn't abruptly stop the output of an entire module. But you can see that it severely reduces the output potential you could get. If we look at typical battery charging voltage somewhere around 13 to 14 volts, you can see that going from a full module to one cell 25% shaded gives you a little bit of loss. One cell 50% shaded, though, knocks us down quite a bit. One cell 75% shaded reduces us by almost in half. We're just talking about one cell out of 33 or 36. Let's go even further. Let's say we had 3 cells shaded in one module. Well, obviously, the effect is even more dramatic. We can look at 3 cells, 25% shaded, 50%, 75%, and 3 cells completely 100% shaded. Notice now again that even in the case of 3 cells, 100% shaded, the module still has an operating curve, but it's pretty low. Most all of our output potential has been lost. An interesting comparison to draw is the difference between all of our shading being in one cell and distributed over 3. Let's look at the case of a certain amount of shading, a certain square inches or square centimeters of shading. But what if it's all in one cell, and what if it's spread out over 3? If we have one cell 75% shaded, we have a reduced IV curve as drawn. If we have 3 cells, each one 25% shaded, that would be the same area as one cell 75% shaded. But notice that the effect on the module is less when we have the shading spread out over many cells. This makes sense. We can draw an analogy to perhaps vehicles on a road where it's a lot worse to have a big blockage in just one place, constricting the flow down to almost nothing. Compare that to having damage or blockage along the road, but maybe confined to only one lane of a 4-lane road. There is blockage, but there's much more flow going by. So you can see that the effect of shading on a module is hard to predict because we have to know the exact geometry of the shading. You can't simply say, what would be the effect on module output if I had 10% of my module shaded? We have to know exactly how is that shading spread over the cell circuit. One of the points that we're trying to get at here is that shading is extremely bad for photovoltaic modules. We have cells connected in series, not just parallel. So if there's a problem with some sort of shading on a module, that shading restricts the output of all the other cells connected in series with it. The effect is very nonlinear. A little bit of shading doesn't cause a little bit of power loss. A little bit of shading causes a lot of power loss. So the first thing that you should have in mind is how to prevent shading in the first place. You should never install your modules in a situation where, especially in winter, when the shadows are going to be long, there are any objects in front of your array that are going to cast shadows on your modules, at least between the hours of 9 in the morning and 3 or so in the afternoon when we have good sunlight. So the first thing you should be doing is installing your system such that your modules are not getting shading from fixed objects. But in the real world, we can't avoid all types of shading. There might be natural causes of dirt and dust, splotches falling on the module, maybe bird droppings that cover up a large area of a single cell, and so on. We simply can't prevent all of those cases from occurring. So what do we do as a manufacturer? We take the responsibility of building into each one of our modules an electronic device a diode. We put it in such a way, and we call it a bypass diode, because it now allows current to bypass around a shaded cell. We install the diodes in each module such that if there is shading on any one cell or a group of cells, the current can actually be bypassed around those cells, flow on to other modules in the group, and avoid the extreme negative effects of severe voltage drop in a shaded cell. Let's take a look at how we actually wire in bypass diodes in our different types of modules. We have two types of designs that we offer, M-series type of module and a Pro-series type of module. In the M type of module, for example, the M55 module, we have 36 cells connected in series. We have 3 strings of 12 that are connected within the module itself. There are 2 locations where we can install these bypass diodes. One diode is installed connecting 24 cells. The other diode is installed covering another group of 24. The middle sort of gets covered twice. If I take my schematic drawing of my module and stretch it out to show me simply a single string of 36 cells, you can see how the diodes cover the module in sort of an overlapping way. One diode starts at the beginning of the module and covers 24 cells. The other diode starts in the middle of that group and covers the other 24 cells down to the bottom of the module. So what we have is groups of 24 cells protected by a single bypass diode. You can see from the diagram how the current might bypass a problem. If we had some cells shaded in, let's say, the upper group, the upper 24 cells, current flowing from the other cells in series with it would start to flow up through this module and then would bypass the shaded string of 24, flow through the diode, come out the end of the module, and then flow on freely to other modules that are unshaded. That's how we get the concept of bypassing the shaded problem. Let's look at our other type of module configuration in our Pro series of modules. Here again, we're dealing with 36 cells. Let's say we're looking at a Pro Charger 4. We have the strings of 9 and 4 of those strings put together. We also now have a location for 2 diodes to be located in our module. But if we take our string and stretch it out into one long string, we notice that now there's not an overlap. The bypass diode at the top protects 18 cells, and the bypass diode at the bottom protects another group of 18, and they're disconnected. In this case, if we had severe shading of some cells, let's say in the top group, current would flow through the first 18 cells of this module, and then flow through the bypass diode and on to other modules. Let's look at a comparison between these two. In the case of the M-series module, the diode takes out 24 cells, so we retain 1/3 of our module, about 33% left in. In the case of the Pro Charger module, 18 cells are taken out, so 18 cells are left in. In other words, 50% of our voltage is preserved. We have different designs based on our junction boxes and so on that we've chosen for our modules. In the actual module itself, you can see in the M-series of modules, the bypass diode is located inside of each of the junction boxes. In the case of the Pro series of modules, we have one single junction box. So in that case, we put both diodes in the junction box. In both module designs, we've chosen to hardwire the diodes into the junction boxes of every module that ships from the factory. Some other manufacturers may indicate in their junction boxes where the diodes would go, but they don't actually install them for you. This is just a manufacturing choice where we feel it's an important enough component to include, for sure, in every single module that's shipped. Let's take a look briefly at a schematic of a 48-volt system to show how the diodes are drawn in or where they exist in a bunch of modules wired together in series and parallel. In the case of parallel wired strings, which I remember don't usually recommend, but some people do, so I want to talk about it just for a second. We would have individual parallel wired groups of 12 volts and then those groups would be wired in series. In that case, you need to install a large bypass diode for the entire group. It's an extra diode that you have to install, and it's a very large one. Why do we have to do this? In the case of severe shading of one of the modules in a group, the other modules in that group are wired in parallel to that module. Parallel wired devices all stay at the same voltage. If the module is severely shaded, it can't produce the current that's required by the other groups pumping into that group. How would the other modules compensate for a module that can't produce enough current? They would try to produce more current. How do they do that? They actually operate further towards their short circuit current point on their IV curve. That gives them a little more current output, but much less voltage output. So the whole string begins to compensate by going lower and lower in voltage. If the compensation is still not enough, all of the unshaded modules will actually pass through their short circuit point and go into a region of negative voltage to try and supply more current. In that case, all of the modules will have gone into reverse voltage, and all of the bypass diodes of those modules will start to conduct. Diodes in parallel is a dangerous thing. Different diodes will start conducting more current before other diodes. And all of a sudden you'll have the full array current from all of the parallel modules flowing through one single bypass diode in one module. It's not designed to handle that much current. It'll probably fail. Then the next diode that's carrying current will fail, and so on. And you'll get a catastrophic failure of all the bypass diodes. The way to get around that, of course, is, well, put in a bigger diode. But you don't need to do it for every single module. Why not just do one big diode for the whole group? Then, if there is severe shading, and the group goes into zero voltage and actually goes into negative voltage, and the diode begins to conduct current around those modules, you have one big diode that's large enough to carry all the current of all the modules wired in parallel. Then that current flows on to the next group, splits up, and goes through unshaded modules. A bit about complexity, and another reason why I don't really recommend wiring systems in parallel groups that are connected in series. If we take a look at a schematic of series wired strings wired in parallel, we can see that what's recommended is that at least one, if not two, bypass diodes are wired around every single module, and if there is any severe shading in one particular module, the current through that string will go through that individual bypass diode and on to the next module in the string. We talked for a minute about bypass diodes. These are diodes that are not normally in the electrical circuit. They only come into play when there's severe shading, and in that case, they allow current to flow around the problem. If the shading goes away, the problem goes away, current flows through the regular cells, and the bypass diode again is left out of the circuit. There's another use of diodes in photovoltaic system design, and we call this a blocking diode. It's the same electronic type of device, the same PN junction, the same physical type of object. But now what's different is its placement in the circuit. Instead of having a bypass diode put in the junction boxes that allows current to flow around cells, we're going to install diodes in series with the module, not in parallel. So current from the modules now will always be flowing through these blocking diodes. What's the purpose of these blocking diodes? A couple of reasons. They prevent leakage from your battery at night back into the array. During the day, modules have enough voltage to push current through a battery. At night, there's no light. The modules don't have any excess voltage above the battery. The battery actually has more voltage than the module. The battery could pump current backwards through the module. This doesn't harm a module, but it does allow for energy loss from your battery. That energy is pretty precious. We don't want to allow that leakage. There are some charge regulators, in fact, many regulators now, either have diodes built in, or they have a relay or an electronic device that stays open at night and prevents this leakage. So perhaps this function may or may not be necessary, depending on your choice of charge regulator. There's another function for blocking diodes, though. They prevent parallel strings from losing power down damaged strings during the day. This has nothing to do with nighttime leakage. This has to do with the fact that if we have parallel wired strings and one module or a few modules in one string are damaged or severely shaded, we could have current from the other parallel strings, instead of going onto their load, going backwards down that shaded string. You wouldn't really notice this, except after time, your battery wouldn't be receiving the charge current that it expects, and your system could fail. So we think about installing blocking diodes, or what might be called isolation diodes, to isolate each one of our parallel strings. An important concern with blocking diodes is that we always have a small voltage drop across the diode during normal operation. Contrasting to bypass diodes, normally they're not in the circuit, remember? Only in case of shading. But for blocking diodes, we have the case where current from our modules is always going through these blocking diodes. We want that voltage drop through that diode to be as small as possible. One way to do that is to use Schottky diodes instead of the standard silicon diodes that are used as bypass diodes. Diodes that are used as bypass diodes can be silicon diodes. These tend to drop about 0.7 to almost 1 volt. But we don't care too much about that because they're not normally in the circuit. Schottky diodes, on the other hand, drop only about 0.3 or 0.4 volts. Since blocking diodes are always in the circuit, we would use Schottky diodes in that case to minimize the amount of voltage drop that we'd experience. Let's take a look graphically at why we might need blocking diodes to prevent leakage from our batteries through our modules at night. It really depends on the exact curve shape of our IV curve. We can look at an IV curve during the day and then that same curve at night. During the day, we have our module connected up to a battery. The battery determines the module voltage. Under daylight conditions, that voltage corresponds to a positive current. In other words, we have current flowing from the plus of the module into the plus of the battery, and from the minus of the battery into the minus of the module. That's proper and normal. What happens at night? Now, the IV curve basically kind of goes to sleep. We still have a module connected up to a battery. The battery determines the operating voltage of the module, but that voltage might be around 12 or so volts. Notice that that causes us to operate on our IV curve in the realm of negative current flow. What does that mean? It means that we have current flowing in the opposite direction, from the battery plus into the module plus. In other words, the battery is discharging through the module. The module has become a load. We want to be able to prevent this from occurring because we've made precious energy from our modules. We don't want to have some of it leaking backwards into the modules and just radiating away at night. Like I said, some regulators may have relays or switches that open at night and prevent that leakage. If we don't have that situation, then you actually have to install a blocking diode to prevent this leakage. In the case of a 12-volt system, we would install a single blocking diode between the plus of the module or modules and the plus of the battery. This would allow current to flow through the diode and into the battery during the day, but prevent electron flow backwards from the battery through the module at night. The penalty that's paid is the small voltage drop across that diode. If we use those Schottky types of diodes and only drop to 0.3 or 0.4 volts, we're at least minimizing that. In the case of a higher voltage system, we have our two scenarios. Remember, parallel wired strings or series wired strings. In the case of parallel wired strings, we'd include a blocking diode as shown. We have a single blocking diode between the entire array and the battery. This would prevent leakage from that battery through the strings of modules at night. In a higher voltage situation where we have series strings wired in parallel, we have a slightly different solution. In this case, instead of installing just one blocking diode, we have a different option now. We can install a blocking diode at the head of every series string. Don't be concerned A lot of people get confused and think, well, I've got 4 diodes now, so I've got 4 times that voltage drop. No. This is what's happening in this case. Current from one string flows through its diode, combines with current that has flowed through its string and flowed through its single diode. And that combines with the next string, which flows through its single diode, and so on. So current only flows through one diode and then combines and flows on. So we still only have a net voltage drop of 1 diode's worth. Wiring our modules in series strings like this allows us to actually perform 2 functions. During nighttime, current cannot flow backwards from our battery into our strings because it's blocked at every string. And during the day, if we had some severe shading on one module or a couple of modules in one string, current from the unshaded modules might try to flow backwards down our shaded string, but it would be blocked by that individual string's diode. The current from the good strings would simply have to flow on out to the battery. So having our modules wired in series strings is beneficial once again. We're able not only to work on individual strings if we need to, but in the case of prevention of leakage and so on, in the case of shading, we not only can prevent leakage at night if we need to do that, but we can also prevent interstring shading problems during the day. In actual field situations, how might we install these individual series string diodes? What's recommended is the wires from each parallel string be drawn out and combined in what might be called a field combiner box or a field junction box. In the diagram, what we can show is that current from each one of our strings here, or 24-volt strings, flows out of each string and individually flows into our field junction box. Within the field junction box, we have the plus wire from each parallel string flowing through its own individual diode. After it flows through the diode, the current combines and flows on. This field junction box also gives us an opportunity to do a couple of other things. The current from the individual strings can be handled by a small wire, but now that it's combined and probably going a long distance, we need to turn that into a much bigger wire. Well, we can do that in this field junction box. The large wire flowing out can be much larger than the individual wires flowing in. Another function that might be performed within that field junction box might be a local disconnect switch. We might also install some lightning protection equipment and so on. So that would be the location where we could conveniently combine many functions, going from small wires to large wires, and also installing individual blocking diodes for each one of our parallel strings. One final note, how big should the diodes be? Again, not physically, but what should be their rating? What should be their current rating? What should be their voltage rating? A general and very simple guideline that I recommend is the diode should be sized to be double the open circuit voltage of the array and double the short circuit current that might be flowing through them. It's a simple oversizing to make sure that when the current is flowing through the diode, it's not overstressed. By way of summary then, what have we been talking about? In previous sections, we've looked at normal performance of modules with expecting full current flowing from them. We based our system sizings on expected average weather. What we're looking at here is one of those problems that we probably can't avoid but want to mitigate as much as possible, shading of our modules. If at all possible, install your modules so that they're not shaded by fixed objects. But in the case of shading that we can't avoid, we as a manufacturer build in bypass diodes into every one of our modules. That allows for current to flow around a shaded area on a module, thereby doing 2 things: minimizing local heating because of the voltage drop there, and maximizing array output because we don't have as much voltage being dragged away by those shaded cells. We also looked at blocking diodes. These are in series with our modules and can perform 2 functions. They can prevent battery current from leaking backwards through our modules at night, thereby losing some precious energy that we made during the day. And even during the day, if we have individual strings higher than 12 volts, we can isolate those strings and prevent current from unshaded strings from flowing backward down a shaded string. In all cases, what we're doing is preserving array output and maximizing system performance. What we're going to look at now in this segment is perhaps one of the most crucial segments we're going to cover. That is the actual calculations involved in array and battery sizing. As we get into the discussion, we'll be supplied with data that we can actually use to make calculations based on the load calculations that we've already made. What we're going to cover is how to integrate some of the principles we've already looked at in terms of battery technology, module technology, and so on. Put them all together, along with our concerns about system design practice, and come up with the actual calculations for how many modules, how many batteries we're going to need to meet our load requirements. There are some basic, simple principles that we'll want to be sure and cover at this point that are the foundation for our choices later on. Some of those principles are listed. The array is sized to replace the load demand. It's based on average weather conditions, though. That's a real important consideration. The weather data that we have to work with is averaged over many years. In any particular sequence of days, you'll have above average days and below average days. So the actual performance of our system will not be average. We're counting on the averaging effect of good days complementing bad days to give us good performance over many years. So keep in mind the fact that the mathematical predictions that you're making at this point are simply averages. They're conveniences for you to use to make a quick calculation. Actual system performance is going to fluctuate plus and minus, plus and minus. So we size the array to meet the load based on average weather requirements. We size the battery to supply energy when the insulation is below that average. The battery is like a big buffer, a big reservoir. If we have an average day, the load usage is met by the array. But if we have days where the insulation is below that average, then the array simply can't give enough energy into the battery to run the load. The battery is slightly depleted that day. The next day, if we have an above average day, filled back up. So the array, on the average, replenishes the battery during periods of insulation that are above average. It's real important to realize that the array is not sized based on recovery time from a period of storms or stormy days. The point is that oftentimes people might think that I want an array size so that after a 5-day storm, my battery will be recharged within 10 days. That is never used as criteria for system sizing. We count on average weather performance, giving us the replenishment of our batteries during good days and a slight decrease in the battery capacity on bad days. We never size our system based on speed of recovery after a period of bad days. If you have a major concern about bad weather, then that's when you should start considering a hybrid system and using a generator for that backup power. We do not design the array to be our backup power. It's our primary power, and it's based on average weather calculations. We size the array based on the worst season in the year. Now, this is another flag in case you have a severe period of bad weather, a month or a few months of extremely low insulation. You should be considering a hybrid system to back you up during those periods. But if you're in more moderate types of weather conditions, you have good weather in the summer and poor weather in the winter. The array is sized based on the worst period of time in that winter period. This prevents your battery from staying at partial state of charge for too long of a period. We can't prevent the battery from being at partial state of charge throughout a year. That's always going to happen. And the danger is, when a battery is at partial state of charge, it's got some lead sulfate sitting on the plate. That lead sulfate can slowly crystallize into lead sulfate crystals. That's what we call sulfation. What we're trying to do by sizing the array for the worst season is minimize that sulfation. We can't prevent it. So the best that we can do is to minimize it. And the way we do that is to look at our load profile and our array output profile, our insulation profile, look at all of these profiles and look at the worst season. Size our array so that it operates the loads during the worst season. Then in the summer, we'll be slightly oversized and our batteries will be fully charged. Again, if this consideration means that most of the months we could operate from photovoltaics, but there might be a few months of extremely bad weather, then we might consider using a hybrid system or a generator. Because in that case, the extra cost involved in putting in modules to get us through that severely bad winter are not spent. Instead, we spend it on a small generator that can get us through that small period of bad weather. Let's take a minute and start looking at the actual calculation process that we would follow. We begin by looking at battery sizing. Then later we'll look at array sizing. We can consider batteries to be full of charge. Now, in actual case, a battery is filled with lead and lead acid or nickel and cadmium materials. But for a conceptual sense, let's think of the battery being full of charge. And when we discharge the battery, we actually lower its state of charge by going down in this diagram. When we recharge the battery, we'll go back up. A battery is sized to operate a load during a sequence of bad days where the insulation is below average, stormy days, bad wintry days. Each day, the array cannot operate the load, so extra energy is drawn from the battery, and the battery state of charge at the end of a bad day is less than 100%. The next day, it's even lower. The next day again, maybe it's even lower, and so on. We typically size the battery bank to build in a number of days of operation, assuming no input at all from the solar array. Now, that's not going to happen. Even on overcast days, we get maybe 5, 10, 15% from the array. But that's very low. We've lost 80 to 90% of what we expected. So, for what we call cloudy days, or days of autonomy, where the system has to stand alone with no input from the solar modules, let's consider no input at all from the solar array. So we want to build into our battery bank a number of days of reserve, enough to run all of our loads for a number of days. How many days? It depends on the severity of, or the criticality of your loads. For residential or non-critical kinds of loads, we often think of roughly 4 to 7 days of reserve being enough. For more critical types of loads, telecommunication systems or critical hospital systems, or anyway, systems that are more critical in nature, we'd want to build in at least 7 to 14 days of reserve in that case. Very important critical telecommunication systems might have even more than 14 days, 21, 28 days of reserve. Given the fact that we've previously calculated our daily load demand, so we know how much we need on a daily basis, and how many days of reserve we want to get us through an expected period of bad weather, we can now begin doing the mathematical calculations for battery sizing. The way we do this is by first considering how much of the battery we can use. We can't use all of the battery capacity. For deep cycling types of batteries, we can only use up to 80%. We want to leave at least 20% on those plates unreacted. For more shallow cycling types of batteries, we can only use up to 50% of those batteries. So 50% remains unused. Now we have the factors in mind that we need to actually calculate battery size. We take the number of days of reserve that we want to build into our battery bank, 4 days, 7 days, 10 days, multiply that by the daily load. That, at first glance, would give you the amount of energy you need in the battery to run your loads. But we don't want our battery to be just that size. We want it to be a little bit bigger so that we are not 100% discharging our battery. So we divide that product by the maximum percent usable from the battery, the 50% for shallow cycling or the 80% for deep cycling batteries. That calculation will give us the battery capacity in amp hours. In terms of number of batteries we need in series to give us the voltage that we need, that's fairly simple. You take the load nominal voltage, the system voltage, and divide that by the battery nominal voltage. For example, you might be designing a 24-volt system and be using a 6-volt battery. In that case, you divide 24 by 6 and end up with 4 modules in series. So we now have the simple formulas that we need for calculating battery capacity in amp hours and the number of batteries that we install in series. Let's look at some correction factors that we want to introduce at this point to slightly modify those calculations. One of the first things we want to do is correct for the fact that we lose capacity when the batteries get cold. At the nominal rating temperature of 25 degrees, a battery has its nominal rated capacity. As the battery gets colder, we lose battery capacity. If the battery warms up again, we'd have that capacity back again. But the point is, we're looking at a system operating in a wintertime condition where we need a certain amount of capacity to give us our days of reserve. And cold weather is taking away some of that capacity from our battery bank. We have to actually size our battery bank slightly larger at 25 degrees so that when it's cold, it has the capacity we need. So we would refer to some sort of chart like this or a specific chart from a manufacturer and read the expected average cold battery temperature in the worst part of the year and use that figure to read on the chart the expected loss of capacity for that battery, for that particular manufacturer. We would then use that battery loss factor in our calculations. Another correction factor that we need to introduce is to take into account the fact that we increase battery capacity as we more slowly discharge a battery. Most battery manufacturers are used to their batteries being discharged relatively quickly in terms of photovoltaics, maybe 2 or 4 or 6 hours, maybe 8 hours for a shift operating a forklift, maybe even 24 hours. Typical discharge times for photovoltaics is measured in hundreds of hours. We discharge our batteries very slowly. So we can look at battery manufacturers' literature and calculate how much more capacity we will have available to us compared to their nominal rating, which might be typically a 10-hour rating. The important thing to remember is that battery capacity increases with slower discharge rates. What we need to calculate is what is our average discharge rate. Certain loads are on, we're discharging at a certain rate. Other loads come on, we're discharging at another rate. We're never truly discharging all the time at the average rate, but that's the number we're going to use. So let's calculate that average discharge rate. We do that by taking the number of days of reserve, 5, 10, 15 days of autonomy, multiplying that by 24 hours a day. That gives us the number of hours of reserve that we're counting on. We divide that by the maximum percent that we're going to use, and that actually gives us the amount of hours, the time, that it would take us to 100% discharge our battery. We're not going to do that. It's just the time that it would take to do that. We can create, or we can then calculate, what we'll call a rate factor, which is the capacity at our average rate divided by the capacity at the standard rate. It's usually the 10-hour rate. So what we're able to do is calculate from our days of reserve and the maximum amount that we're going to use, calculate the amount of time that it would take us to discharge our battery. Typically, this turns out to be 100, 150, 200 hours. We then look at battery literature and can compare the capacity at that slow rate to the capacity at the manufacturer's standard rate. When we divide those numbers, we'll calculate what we've called a rate factor, and we'll use that rate factor in our sizing calculations. Another correction factor or limiting factor that we have to include in our calculations has to do with temperature again. But it's not just the loss of capacity due to colder temperature. This is a critical factor. This is looking at the possibility of the battery actually freezing. Normally we'd say that, let's say, a deep cycling battery can be discharged 80%, and we count on using that 80%. But we can't always do that. If the battery temperature gets so low that the electrolyte and the water combination might freeze, the freezing process would expand and the battery would be damaged, perhaps forever. So we don't want to allow our batteries to freeze. We've got to look at the expected lowest temperature and, using a chart such as this, calculate the maximum depth of discharge that we can go to. The chart really begins at about -8 degrees centigrade. So if your battery coldest temperature in the year is going to be warmer than -8 degrees, you don't have to worry about this factor. But for those that are installing batteries in truly cold climates, if the battery temperature is going to get lower than about -8 degrees, you've got to back away from a deep discharge. Notice that, let's say at roughly -20 degrees C, the battery gets that cold, leading up off the chart and then across, we read a little bit more than 50%. The battery can't be discharged more than about 50%, not 80%. We've got to back away from that deep discharge limit, because if we went deeper, even using a deep discharging battery, the electrolyte would freeze. So this calculation factor is for those climates that are extremely cold, and we need to correctly estimate how cold the battery will get, back away from our maximum depth of discharge factor that we may have already been planning on using, like 80% for a deep discharging battery, and use only that amount that is safe to prevent the battery from freezing. If we take into account all of the correction factors that we've been talking about, we can now do a more precise battery capacity calculation. Let's look at that formula. We have our number of days of reserve times the daily load. This at first gives us the amount that we need in our battery bank. Then we divide by the maximum percent usable. We also divide by the temperature derating so that we install more battery capacity than we need at 25 degrees, so that when the battery is extremely cold, it will have the capacity we really need. And we also divide by the rate factor, so that we install only the capacity that we need. If we discharge our battery at a very slow rate, we'll now have the calculation for the amount of battery capacity we need to buy at 25 degrees, and at a standard discharge rate of, let's say, the 10-hour rate. So that as we're slowly discharging our battery, we get the full capacity that we expected. When you're choosing your battery design, once you've done your calculations of necessary battery capacity, you have to go one step further. You have to actually choose a particular battery and then maybe put a number of those together in parallel to give you the capacity that you've calculated, and put them together in series to give you the voltage that you need. How do you choose that battery? You have a wide number of choices typically. If you look at battery manufacturing literature, different manufacturers will have many choices at different capacities, and perhaps even at different voltages. So what guides you to choose which particular battery? This is a decision that you can make, and another designer would make a slightly different decision. They would all be correct. So the guidelines that I have to offer you simply are some sort of outer bound guidelines and reasons for choosing a particular number of batteries. Let's say you've done your system sizing calculation and you have to install 1,000 amp hours of battery capacity at 24 volts. Well, do you choose one 1,000 amp hour battery? Or do you choose maybe two 500 amp hour batteries and put them together in parallel? Or four 250 amp hour capacities and put four of them in parallel, and so on. The guideline that I'd like to give to you is simply choose them big but not too big. In other words, you want to choose large capacity cells so that you minimize the number of batteries that you're connecting in parallel. We want to minimize the number of parallel connections. You can go to the extreme and simply choose one large battery, so you have simply one string of batteries. A lot of designers prefer that. Others say, well, I don't like putting all my eggs in one basket, so I would like to at least have two strings. So let's say in our case of calculating 1,000 amp hours of battery capacity, you'd choose batteries that have roughly 500 amp hours of capacity and put two of them together in parallel. Then you'd have two strings. The reason for that is if there's a failure or a problem and you need to work on one string of batteries, you can disconnect it and still have another string that allows your system to operate. I don't draw too strong of a distinction between the one solution or the two solution. Either one of those I think is acceptable. The real question for me is, how many can you have in parallel? How big of a number can you go to? Can I have 10, 20, 50 batteries in parallel? The answer to that is no. You want to minimize that number in parallel. So a guideline that I'd like to give you is to have perhaps at least two parallel strings so that you have redundancy, but no more than, let's say, 6 or maybe even up to 8 batteries in parallel, but no more than that. It's a rough guideline. It's not a rigid rule. But if you find yourself designing a system with a small battery, let's say a battery that has only 100 amp hours of capacity, and you want to install 1,000, you need to connect 10 of those in parallel. I think that's too much. So if you can use a rough guideline of approximately 6 or 8, something in that range as a guideline for how many in parallel, I think that will guide you in terms of choosing the capacity that you need. We've looked at battery sizing and using the form to calculate battery to meet our reserve requirements. The other part of system design involves array sizing. So now we're going to go through the relatively simple steps involved in calculating array size. How many modules do I need in parallel and in series to operate my load? The calculation, the formula is really quite simple. What we're basically looking at is the daily load demand that we've calculated we need to supply every day, divided by what one module can deliver in a day. It's simple. If we need a certain amount of amp hours to operate our loads in a 24-hour period, we look at what one module can give us under the few hours of sunlight that it'll receive. We divide, and that tells us the number of modules in parallel, the number of modules we need to connect to give a current flow so that the battery is fully charged up in the few hours of sunlight that we have. In order to calculate the number of modules in series, we look at the system voltage, the load voltage that we've decided on, 12 volts, 24 volts, whatever that may be, and you divide that by the module nominal voltage. In all cases with power systems that you're designing, that would be a 12-volt module. So with these simple formulas, we can calculate the number of modules that we need to connect in parallel to give the current flow to recharge our batteries, and the number of modules to connect in series so that as that current is flowing, it has the voltage that we need to charge our battery bank. We need to expand on these simple formulas just a little bit. There's a few details I want to add in and explain. When we're calculating the number of modules that we need, the question would be, well, my weather varies throughout the year. Which time of year should I use? In general, you should look at the worst season, the worst month of output. If we calculate for the worst season, the season in which we have the least solar insolation available, and we can still operate our loads then, we'll be able to operate our loads anytime during the year. We have computer programs that allow us to predict, based on actual measured data that we've measured at a site, these computer programs allow us to predict the module output. We can also use another technique called a peak hour method. We'll go through both of these methods and allow you to estimate how much output you get from one module. Once you've estimated the output that you get from one module, don't use that output. You should derate that output by about 10%. In other words, we can calculate with our computer programs to the nth degree, very precisely, an estimation of what the module will give. But don't count on that. We're dealing with the weather. You don't know what's going to happen. You could have a bad month, a good month, a bad year, a good year. You don't know. You could have dust and so on accumulating on the modules during a dry season. Maybe that's washed away during the wet season. In other words,
you want to build in an engineering safety factor in your calculation, and we recommend at least 10%. So with the numbers that you'll have for estimating module output, you derate that by 10%. In other words, you multiply by 0.9. That gives you a safety margin in your system design. And finally, there's another factor we've got to take into account. It's almost like a small load. The modules are creating current that's flowing into our batteries. That's being stored. Then it's being released from the batteries at night, let's say, and running to the load. We need to take into account the inefficiency of the battery in its ability to store and then redeliver charge. We call that the battery charge efficiency, or the Coulombic efficiency. That typically in photovoltaic systems can be estimated to be about 5 or so percent, 10% in extreme conditions. So the general factor I'd recommend is using about a 5% battery charge efficiency factor. So we'll look at our estimated module output, and we'll derate that due to dirt and dust and possible aging and just an unknowns that might occur. And we'll also modify our equation with this battery charge efficiency to effectively increase our load slightly to overcome the battery charging inefficiency. So what this leads us to is our final equation for calculating the number of modules that we need in parallel. We have our daily load demand. That's what we need to supply every day. We divide that over here by the charge efficiency. You can now see that if we're dividing by our charge efficiency of about 0.95, we're effectively increasing our load by about 5 or so percent. That's taking into account that battery inefficiency. Then we also divide by the module output multiplied by that derating factor of typically 0.9. In other words, we're reducing our module output by about 10% to be on the safe side. If you have a seasonal profile, you should calculate your array needed for each season and then choose the largest array that you're going to need. So let's say that you've got a load that peaks in the winter time. You would look at the output of your module in the winter time and calculate the number of modules you'd need to meet that load. If you had different loads in summer and winter and different module output in summer and winter, you need to calculate at least 2. You don't have to do all 12. At least look at the load demand in the winter and the array output in the winter, and calculate the number of parallel modules. Then look at the load demand in the summer and the module output in the summer. Calculate the number of modules you need there. Let's say you did this calculation and you came up with needing only 7 modules in the summer, but needing 9 modules in the winter. Well, you'd size your array for 9 modules. You'd have a little excess in the summer. So now you've got the tool to do your calculations for the number of modules that you need in parallel and the number of modules in series. A question comes to mind, which type of modules should I use? We make modules that have both 36 and 33 cells connected in series. These give different voltages. What's a rough distinction between these two types of modules? What guides me in terms of choosing these? The basic guideline that I'd like you to follow is a temperature concern, really. Modules made with 36 cells have enough voltage to fully charge a 12-volt type of battery, even when they're very hot. At 25 degrees C, standard room temperature measurement, our 36-cell modules have a max power voltage at around 17 or so volts. When they get hot, up to about 50 degrees, which isn't untypical at all, we lose some voltage and we have about 15 volts. That's enough to charge a 12-volt battery. So 36-cell modules should be used in the most hot of climates. These can also be used when they're directly coupled to DC motors or when they're used in utility interconnected systems with max power tracking devices. Why? Because when we're connected up to a DC motor or to a max power tracking device in a utility inverter, the motor and the max power tracker can extract all the power that we deliver with those 36 cells. A battery cannot. Remember, a battery holds us back in voltage to around 13 or so volts, and the max power voltage might be around 15. A motor or max power tracking device can operate at around 15 volts and use all that power. So That's a good match with a 36-cell module. A 33-cell module produces at 25 degrees about 16 volts max power voltage, and when it heats up to 50 degrees C, it has about 14 volts. This is still enough to charge a 12-volt battery, but we shouldn't operate these modules in the hottest of climates. You can see we begin with 3 less cells in the first place. So 33-cell modules should be used in moderate climates. In other words, not the hottest climates. They're useful for general battery charging. We've designed them so that in most climates around the world, a 33-cell module will be acceptable. A 36-cell module should be chosen for the hottest of climates or for industrial applications where we need absolute assurance that we have the most output from the module under all conditions. In order to proceed with your system sizing calculations now, you need to have an actual number for module output, amp hours per day, from a particular module in a particular location. Siemens Solar has a variety of computer-based tools that we can use, and we've collected actual weather data from over 2,000 sites around the world. We use our computer programs to estimate module output starting from actual real weather data, real hot climates, real weather that varies summer and winter. And using the computer programs, we estimate the change of insolation over time, the change of temperature over time. We can use these calculations to predict module IV curve, hour by hour, and matching those up to the typical load that will be used, in most cases, batteries. We can predict actual module output in amp hours per day. Programs that we use are our program called SASE-B, standalone systems with batteries, SASE-M, standalone systems with motors, and PV system, which allows module estimations in a variety of situations. We use these programs and have used them to create the data that you have in your notebook. You can now choose a location and choose the lowest output in the year for that location and proceed with your array sizing calculations. There's another method for estimating module output that I want to cover. It's called the peak hour method, and this is often referred to by people. I want you to be familiar with what it means, what the definition is, and how accurate or inaccurate it might be. If you don't have a computer program available to do your system sizing, but you do have measured weather data on a tilted surface, you can use this method to roughly estimate the module output. It's an approximation, but given the complexities of guessing the weather, it's a useful calculation. What it involves is taking weather data that actually fell on a real surface, which varied minute by minute and hour by hour, and making a gross approximation. What we do is we pretend that all of the insolation that is measured at a real site fell at the peak rate. It's as if the sun from darkness turned on and shined at 1,000 watts per square meter for a certain number of hours, and then shut off. Of course, this didn't really happen. The light level varied hour by hour, minute by minute. But it's an approximation. Why do we do this? Because we know module output at peak level, at 1,000 watts per square meter. It's in all manufacturers' literature. You don't know module output at 9:30 in the morning. You don't know what that insulation was. But you do know what module output would be at 1,000 watts per square meter. That comes from the manufacturer's literature. Let's look at an example, and you'll see how simple this is. Let's say that a particular month you have measured data on a tilted surface, and in a particular location for that month, let's say 4.5 kilowatt hours per square meter was measured. That's the total amount of insulation accumulated over a day. It's as if, or we can rewrite that as 1 kilowatt per square meter times 4.5 hours. It's the same number. But what is 1 kilowatt per square meter? That's 1,000 watts per square meter. That's peak insulation. It's as if we got this 4.5 kilowatt hours per square meter by light shining at 1,000 watts per square meter for 4.5 hours. So we call this our peak irradiance, and we call the number of hours the peak hours. We would then take those peak hours and multiply them times the peak current output of the module, the max power current of a module. For an M55, for example, that's 3.05 amps. And in this case, we would calculate 13.5 amp hours per day in that particular month from that module. It's another rough approximation technique given insulation data and if you don't have a computer program. It's helpful to clarify this concept by looking at it graphically. Let's take a look at an actual irradiance profile for a location and look at what the peak hour estimation might be for that location. As an example, we can look at Phoenix, Arizona in the United States in April. The insolation profile that we would typically predict is shown, starting at 0, rising to a peak in midday, and falling off again in the afternoon. We look at the total area under that dome-shaped curve. That comes to be 7.3 kilowatt hours in that particular case. We create a rectangle that has a height of 1 kilowatt per square meter, peak irradiance. And we have that rectangle span a period of 7.3 hours. The area under the rectangle is the same as the area under the sloping curve. And now we see that the peak hours that we have available to us is 7.3 peak hours. We would use that number and multiply times the peak current of the module we wanted to use. In this case, we're looking at Phoenix, Arizona, but in December, a lower insolation month. Again, we have a dome-shaped irradiance profile from morning to afternoon. The area under that curve would be 5.2 kilowatt hours accumulated in a day. We create a rectangle again with a height at 1 kilowatt per square meter, peak insolation, but now the width of the rectangle is only 5.2 hours, so that the area under the rectangle is the same as the area under the actual curve. So what we're estimating here is that we have roughly 5.2 peak hours of insolation available. We would multiply that times the peak current of a module to get an estimation for amp hours per day per module. This is an approximation method. What are some of the weaknesses involved in this peak hour approach to system sizing? First of all, there's no temperature being taken into account, and we know that higher temperatures reduce module output. So if we had two locations, both with similar insolation in a month, but one was much hotter, the module outputs would not be the same. But this technique would predict that they would be the same. So that's a bit of an inaccuracy. Module output characteristics also change at very low light levels. Inherent in this technique is the assumption that every photon, every bit of irradiance that falls on a tilted surface turns into current flowing into a battery, and that's not always the case. Also, as the sun moves around a module, the angle of incidence causes reflection off of the glass, and that's not taken into account here either. And finally, we know that batteries actually operate modules away from their max power current, and yet we're using that max power value in this calculation because it's in the literature. So these factors lead to some slight inaccuracies in this method. It's useful for rule of thumb, back-of-the-envelope types of calculations, but to really get a good system sizing calculation done, you should rely on computer prediction. After you've done your calculations for array and battery sizing, there's a couple of checks or calculations that we can perform that I recommend just to give yourself a reality check, not only to check your mathematics, but to give you a sense of a couple of parameters of system design that you've created, checking yourself to make sure that this is what you expect. One of those checks involves calculating the actual or sort of expected average daily depth of discharge. You may have decided to use a deep cycling battery, but what we're checking is, on the average, what will be your actual daily usage from that battery, the daily or nightly depth of discharge. Easy to calculate. You take the daily load that you've previously calculated and divide that by the actual full capacity of battery that you're going to install. The number of batteries in parallel times the single battery capacity in amp hours. By doing this calculation, you'll get an estimation in percentage of the amount of battery that you use. This might be as low as 10% for a system that has many days of autonomy. So that would bring you back to knowing, even though you're using a deep cycling battery, how shallow you're actually using it on a daily basis. The other check calculation that I'd recommend you do is to check for the maximum rate of charge. You've designed an array, you've chosen a battery size. You've designed the array based on daily recharging, and you've sized the battery based on meeting certain days of reserve requirements. The question is, how do the two match up? Have you designed the battery bank too small or the array too big so that under peak conditions during the middle of the day, the array would be charging the battery too quickly? Typically in photovoltaics, this never occurs as a problem, but it's an important check. You calculate this by, again, calculating the total capacity that you've actually installed, the number of batteries in parallel, times a single battery's capacity in amp hours, and you divide that by the total peak current that might be flowing from the array. The number of modules in parallel times the max power current of a module. When you finish doing this calculation, you then have a charge rate that will give you an indication, compared to manufacturer's literature, of the sort of peak maximum rate that might be flowing from the array into the battery bank. If this is slower than the maximum charge rate recommended by the manufacturer, then your system size is just fine.